But there is a lot that applies to amateur radio, and it depends a lot on how you operate. For the most part, I don't worry about propagation because I'm just a ride chewer and I get on there. If the band's open, I hear somebody, I talk to them. If you're a dedicated DXer or a contester, that puts a little bit different emphasis on what you need to know about it. When I was in the military, it was critical. That was a long time ago before we had much satellite communications. HF was the only link you had back to the real world, as we called it. And the same thing for the commercial guys. Back before everything went satellite and other means of transmission, if they were long haul stuff was HF. Millions of dollars and many people have spent many lifetimes studying HF propagation and working out the HF propagation prediction programs. Again, we amateurs benefit from that, but they didn't do it for us. There were other reasons to do it. We're going to get into some stuff that's way above my grade, and we won't get into it very far. We'll get into some stuff that some of you are going to consider very, very simple and simplistic. I don't know any other way really to cover it. A good reference book is the ARL Antenna book. Chapter 4 covers propagation. It's up to date, very well written, tremendous amount of information in there. The book comes with a CD, DVD, whatever it is, CD it says on it, which of course contains everything in the book plus a bunch more. And I've installed it on that computer as it wasn't any problem. Some of it includes propagation prediction and that sort of thing. Hopefully we'll get to that a little bit later. But that's one of my main references. There are others. This one's written by a guy up in Alaska called Receiving Antennas. He's a notch or two, again, above me electronically. He works with the guys at HARP and those kind of places, the physicists, and he understands some of that stuff. But he can provide a lot of good information, and he's pretty good at writing, so the rest of us can understand it. And if you want to really get above your pay grade, ARL's got a book called Propagation and Radio Science. Again, they can lose you in the math and stuff real quick when you get into that, but so I don't get into it. But you can still get a lot of information out of it. I'm going to start off rather simply. To understand HF propagation, you've got to understand what they call the ionosphere, because that's where it takes place at. And if you look at the Earth, as you go on up higher, you got different layers. The troposphere is what we live in. That's where all your weather is. That's the lowest layer. You get above that, you get into the ionosphere, which goes up to outer space. The ionosphere is what we depend on mainly for HF propagation. I guess why they call it the ionosphere is because it's filled with ions. What's an ion? That's an element, an atom that's missing an electron. It's those missing electrons which are floating around the ionosphere that bend our signals back down to Earth. They are caused by ultraviolet radiation from the sun. It hits these atoms and splits off an electron. And I mean, it's just amazing that this works at all when you think about it, because there isn't much up there. All the thick air and all that stuff's down here near the Earth. It's very, very thin up there. And for that reason, it's very difficult to study it. And they've had to put a lot of money and time into that. You've got multiple layers to deal with. I mentioned the troposphere where we live. That's only going to affect propagation when you've got a thunderstorm on top of you, or these kind of things. But as you head up, the first layer you hit is called the D layer. As far as radio propagation is concerned, it's worthless. All it does is absorb your low frequency signals. You can't work 160 or 80 meters during the day because of the D layer. Your signal goes up there, and instead of coming back down or going through it, it just absorbs it. And that affects 160, 80, and to some extent 40 meters during the day. It is strictly a daytime layer. When the sun comes up, the D layer starts to form. When the sun goes down, the D layer goes away. Not quite as fast as flipping a switch, but close. So as soon as it gets dark, you can use these low frequencies again because the D layer is not there to block them anymore. But it does affect the low HF propagation. And then as we get past the D layer, we hit the E layer. The E layer is just not dealt with much when it comes to propagation because all it does is basically the same as the D layer. It kind of absorbs the signal, the lower frequency signals. It doesn't reflect anything back down. It's just kind of ignored. It just doesn't have that much effect. The D layer is a much greater signal absorber than the E layer is. Sporadic E, man, we could spend a month on that. It drives the propagation guys crazy because most of the time you don't have any sporadic E layer. So when you don't have it, of course, you don't worry about it. The signal just goes right on through up to the F layer, which is what counts. However, until about the middle of August, for about 2.5 months, we had sporadic E almost every day. Sporadic E, I found out, surprisingly, has a great effect on HF propagation. If you've got strong sporadic E, it will reflect your signal back down. But you see what that does to your coverage distance. Because the E layer is so much lower, it doesn't go nearly as far as if you get up there into the F layer. I got a bug to work 17 meters this summer. I put together a 3-element monoband out of some parts left over from other antennas and stuck it up there. Never played around with 17 meters before. It has 18 megahertz range. And I was amazed because I work, and I was just doing this in my spare time when 6 meters was dead, which is my primary band. I worked 46 states this summer on 17 meters. This is why I worked them, because short skip, thanks to the sporadic E. Otherwise, if I was working 17 with F2, my first hop lands out in the West Coast. Really, I work California every day. California, Oregon, Washington State, Hawaii, no problem. But any place closer, the F hop is just too far. But the sporadic E allowed me to work all those states this summer, which is a benefit if you want to do something like that. But if you're trying to work Europe, you got a problem because your signal won't go that far. So people consider the band to be dead. When there is no, when there is no sporadic E, of course, the signal just goes right on up there, like when there's no D, or E goes on up to the F layer. But the sporadic E will often block the signal. But one of the things you have to understand about sporadic E is it is not normally widespread up in the ionosphere. You can have what they call a sporadic E cloud over part of the eastern United States, for instance. So when I get on 17 meters, I can work guys on the East Coast, Northeast, with no problem off sporadic E, single hop sporadic E. I can point the beam out west and work Hawaii and California because there's no sporadic E out west. So I'm going right on up through to the F layer. This makes things a little bit difficult from a propagation prediction standpoint, and basically they just ignore it. But that can cause you some problems because the prediction program will say, well, you can go ahead and use this frequency and it'll work fine, and you try and use it and it doesn't work fine because you got sporadic E and it blocks it. So that can cause a problem there. But I don't want to dwell too much on E and sporadic E. Sporadic E exists 2 to 3 months out of the year, mainly in the summer, June, July, halfway through August this year. We'll see a little bit around Christmas again. The rest of the time it's not there, so it's not an issue. The F layer is there all the time. I show an F1 and an F2. Sometimes you have 2 layers during the day. Sometimes you just have one, which I call the F layer. At night, the two normally combine and you just have an F layer. All of this layer and ionization activity, again, is caused by the sun. And you've got to take that into consideration when you're looking at HF propagation. Depending on where the sun is going to depend on where you can talk. Because once the sun goes away, the ionization starts going away too. One of the things we'll run into, and we'll look at this later on the ionograms, the propagation prediction has to be made based on the path that you want to work. If I'm here and I talk to this guy here, the propagation here and here doesn't make any difference. What makes the difference is the propagation here, where the signal is going to be reflected back from the ionosphere. So if it says your maximum usable frequency is 30 megahertz from here, that doesn't mean that I can get on 10 meters and work this guy over here, because the maximum usable frequency up here might be 20 megahertz. So if I want to work this guy here, I'm going to have to get on 20 meter band, 14 megahertz, something below 20. So what counts is what the ionosphere is doing up here where your signal comes back down, not particularly where you're at. This causes some problems, as we'll see later. But they have so many ionospheric sounders and stuff out there these days, and so much computer software that they can, even though they don't have a sounder here that tells you exactly what it is, they can still predict what it's going to be here. So as long as you know where you are, and as long as you know where the station is that you want to talk to, you can use the propagation prediction software to find out whether or not you can do it. Now this is very simplistic. It kind of looks like your RF signal going out there is a laser beam, right? It's not. You got to understand that. Your RF signal, even from a beam antenna, is a cone or fan shape. If you look down on top of the beam, you're radiating out something like that. You cover this whole area. If you look at the beam sideways, again, you've got a cone coming off of it here. So you're not sending a single ray up there. This is not well drawn, but it gives you an idea what's happening. You're transmitting here, you're hitting the ionosphere in a bunch of places here, and you're coming down in a bunch of places over here. That's why you can point your beam towards Europe, and you can work every country in Europe, because your signal is not coming down just in one little place, one little footprint. By the time it gets there, it is spread out over a huge area. The fact that they can hear that signal spread out like it is amazing. I mean, they're so weak, it's unbelievable. But it works. And not only that, but you can work multiple hops. I just show one hop here. But the ground, or even better, the water, will reflect that signal back up again, and it can come back down again farther away. On sideband, you can work up to 3 hops if conditions are good. That's a long ways if your hop is 2,500 miles. 3 of those get you out there a long ways. Digital modes, you could work 4 hops, just because the signal decreases greatly with every hop. But you could work 4 hops. They detected as many as 5 hops, but I don't know if you could use that for communications. I routinely work 3 hops every summer into Europe on 6 meters. And it takes me 3 hops normally to get there. First hop comes down in the Northeast, the second hop comes down in the Middle Atlantic, third hop comes down in Europe. Those signals are normally about 5 and 3, with 3 hops like that. Whereas a single hop, the guy up in the Northeast, where the first hop comes down, he's 20 or 40 over 9. But by the time you get to that third hop, you can just barely pull him out of the noise. Okay? That's just the way it works. And this is a very simplified discussion, because if you've been around amateur radio very long on the HF bands, you'll realize that strange things happen. The ionosphere is constantly changing because of the sun. It's constantly moving. So it's not stable. It's constantly changing. Sometimes it will do unexplainable things, like it might decide to duck your signal. It's down over here. Instead of a normal single hop, you get a double hop on as strong as a single hop. They don't know exactly how it does that or why it does it, and they can't predict it, but it evidently happens. Have you ever heard of long delayed echoes?
Isn't that where the signal wraps around the world and comes back to you in the back?
It appears to, and it may wrap around more than once. You hear a signal a long time after it's been transmitted. They can't explain that either. They have theories for it. But the point I'm trying to make is it's not as simple as this looks here all the time. But this covers the way it works most of the time, which is what the commercial guys and the military guys need to know. And that's what the propagation prediction software is based on. Now, I gave you two handouts. One of them is that anything important? Okay. One of them is a picture of an ionogram, and I got that from this particular one from Wikipedia. You have things out there called digisons or ionosons. What they are is simply a radio broadcast station. They can be located any place. There's about 150 of them. And you can pull out the map. You can find all this stuff, via Google or whatever. But what they do is they send a radio signal straight up, 90 degrees. And they got a calibrated receiver that picks up what comes back down. And that's what you see on this ionogram right here, is the results of that. And they sweep the frequency. So they get an idea of what the ionosphere is doing at that particular location. Keep in mind, these are physicists that are using this stuff. So don't expect it to be obvious, even with the explanations they give here, as to what you're seeing. I can't explain half the stuff, probably 3/4 of the stuff on here, but I know enough to get some usefulness out of it. And that's what I'll try and share with you. If you look at the graph, you've got on the bottom across there, you've got the frequency, transmitted frequency. The other graph going up, the vertical one, is the distance above the Earth where that signal is reflected back down from. And of course, to calculate that, all you have to do is measure the delay in time from when you send the transmitted signal out till it comes back down again. You're not going to do that with a stopwatch. These signals travel at the speed of light, basically. But we have digital computers and clocks and all that stuff that can handle that. So what you see here, all these specks or whatever you want to call them, some of them are green, some of them are red, we'll get to that, are computer indications of where that radio signal was reflected back down. And you can gain a tremendous amount of information from that when you go processing it with a computer. Something to keep in mind though, when you send the signal straight up, it is much more likely to go right on through the ionosphere than to come back down again. The more of an angle your signal hits the ionosphere at, the better chance it's got of coming back down again. So when you look at this ionogram here, you'll see that there's nothing coming down above 6 megahertz. And that's normal. Because, again, they're shooting the signal straight up. But if you look over here, and you can look in a couple different places, it shows up there that the F2 FOD is 4.8 megahertz. That's up on the top left there. And that's based on the reddish colored spots that you see. You can see it right there below 5 megahertz, there's a bunch of reddish spots. that's the F2 layer, okay, that's reflecting this stuff back down. And you can see the layer is very thick, and stuff being reflected down from hundreds of miles up. And as far as the height of these layers, D layer probably around 60 miles, E layer normally is around 100 miles, sporadic E layer is normally normally a little bit higher than the E layer, maybe 125 miles. Sometimes they're the same heights, and a few times I've seen them lower, about 90 miles. This stuff is changing constantly, bouncing around. Same thing with the F1, F2 layer, F layers. If you look at this same sounding 5 minutes later, it'll be a little bit different. The ionosphere is constantly changing as the sun constantly is moving. Actually, the sun's not moving, the Earth is, but it appears the sun is moving from east to west. The ionosphere is constantly changing. Now, what this, this tells you what you can expect from an NVIS, basically, signal going straight up or close to it. As the distance gets farther away, though, the maximum usable frequency, which is the MUF, increases. So if you look at this, they got a little line down here on the bottom left that goes across. It says D, which is distance, and then MUF, which is maximum usable frequency. What that says is that 3,000 kilometers